Hi, my name is Mehira Alla, and I'm a student at Liberty High School in Frisco, Texas. This is my presentation for the International Young Researchers Conference. My project focuses on applying machine learning, specifically combining models through ensemble techniques, in order to analyze images of stem cells in various stages of differentiation and improve early cancer detection. So first, what are stem cells? Stem cells are unspecialized cells with two defining features: self-renewal and differentiation. They can generate various specialized cells in the body and are primarily found in the bone marrow. Because of these properties, stem cells are used to regenerate tissue and treat diseases like leukemia, autoimmune disorders, and cardiovascular conditions that were once thought to be incurable. As a result, stem cell technology has become a cornerstone of regenerative medicine. Today, over 80,000 stem cell transplants are performed annually worldwide, with that number growing by about 6% each year. However, in spite of their potential, stem cell therapies carry serious risks, especially when it comes to the development of cancer. Stem cells' high rate of proliferation is what makes them very effective for healing, but it also makes them highly susceptible to genetic instability. During differentiation, they can accumulate mutations, and some may drive transformation into cancerous cells. Embryonic stem cells, in particular, are known to cause teratomas, which are tumors that grow aggressively and controllably. For transplant patients, especially those receiving allogenic transplants, relapse is a major concern. The 5-year survival rate for these patients can be as low as 22%, and most experience relapse or death within 2 years. This makes the early detection of mutations critical, as it can be the difference between long-term remission and recurrence. Detecting early-stage cancerous changes in stem cells, however, is not an easy task. Traditional methods are often time-consuming and error-prone. Human interpretation of images can also be inconsistent, particularly when analyzing subtle morphological differences, and even highly trained specialists can disagree. As a result, tumors often go undetected until their later stages, which significantly compromises patient outcomes. This has led some researchers to turn to machine learning for more scalable and accurate solutions. Machine learning offers the potential to automate the identification of cancerous cells and reduce the reliance on manual image reviews. However, many past studies using ML techniques have struggled with overfitting, low generalizability, and limited interpretability with their models, especially when dealing with high-dimensional medical imaging datasets. Interpretability, in particular, remains a major barrier to clinical adoption, since physicians really need to understand how and why a model makes its predictions. This brings me to the objectives of my research. My study aimed to take steps towards the early detection of cancerous mutations in stem cells by classifying images from different stages of differentiation, using ensemble learning to enhance diagnostic accuracy and inform clinical decision-making with greater interpretability. I then plan to compare whether a stacking or averaging technique was more effective in this scenario, given a simpler binary image classification task and their opposing strengths. So, for context, ensemble learning is a machine learning technique that combines the predictions of multiple models to make a final decision. This approach often leads to better accuracy and reliability than using a single model alone. The ensemble methods that were evaluated in this study were averaging and stacking, as I mentioned earlier. In the averaging ensemble, each base model makes a prediction by outputting a probability between 0 and 1 for each image, which gets averaged across all 3 models. If the final value is greater than 0.5, the ensemble classifies the image as class 1. If it's 0.5 or below, it classifies it as class 0. This way, even if one model makes an incorrect prediction, the other 2 can offset it, leading to a more reliable final decision. In contrast, stacking is a more complex method. In this case, a logistic regression meta-learner is trained to combine the outputs of the base models in a way that optimally balances their strengths. This allows the ensemble to learn how much weight to give each base model under different conditions, creating a more accurate final prediction. So the models I selected for this study include 2 traditional machine learning classifiers, which were support vector machines and random forests, and a deep learning-based convolutional neural network. These 3 models were chosen because they each bring different strengths. SVMs are particularly well-suited for binary classification tasks. Random forests are highly interpretable and good at handling structured data, while CNNs, on the other hand, are ideal for learning complex spatial patterns in image data specifically. So the dataset that I used consisted of 972 images of cancerous stem cells that were taken from a publicly available Kaggle dataset. Each image was labeled based on whether it represented an earlier or later stage of differentiation, and that served as the binary classification label. So the training began with the images being pre-processed through normalization and resizing to ensure that they had consistent input dimensions. To help the models interpret the image data more effectively, I tested two feature extraction methods, VGG16, which is a convolutional neural network that's retrained on ImageNet, and HOG, or histogram of oriented gradients. After evaluating the performance using both feature extraction methods, I moved forward with the VGG16 since it provided superior results in capturing the image features that were relevant to the classification. Once the features were extracted, the dataset was split into 80% training and 20% testing data. Each of the three base models were then trained individually using these extracted features. Following this, the ensemble techniques were implemented. In the averaging ensemble, the prediction probabilities from each model were averaged, and any value above 0.5 was classified as a positive prediction. In the stacking ensemble, the outputs of the three base models were fed into a logistic regression classifier, which learned the optimal combination of inputs to produce the final prediction. To evaluate the performance, I used accuracy scores, cross-validation scores, classification reports, confusion matrices, and ROC curves. These metrics allowed me to measure not only how many samples were classified correctly, but also how well the models distinguished between true positives and false positives, which is especially important in a medical diagnosis where false negatives could be life-threatening. So the following slides contain the tables showing all of the collected metrics for each model. The first table looks at the feature extraction method used, the accuracy, and the training time. The second table looks at the accuracy, precision, F1 score, and recall. And the third table looks at the mean cross-validation accuracy and the standard deviation. So to go over the most important data, the SVM achieved an accuracy of 86.12%, the random forest reached an accuracy of 85.05%, and the CNN performed the best among all the base models at an accuracy of 87.16%. With mean accuracies around 0.81 to 0.82 and low standard deviations, the cross-validation scores also suggested that the models were generalizing well across the dataset. Now looking at the ensembles, the averaging ensemble reached an accuracy of 90.39%, while the stacking achieved an accuracy of 96.85%, which was the highest of all of the models, both the base and ensembles. Now looking at the confusion matrices, it showed that the SVM misclassified 17 class 0 and 22 class 1 samples. The RF misclassified 18 and 24, while the CNN had 12 and 24 misclassifications respectively. While the CNN led in accuracy, all of the base models struggled with some of those borderline cases. Now looking at the ensembles, the averaging ensemble misclassified 13 class 0 and 14 class 1 samples, while the stacking ensemble performed the best with only 11 class 0 and 9 class 1 errors. These reductions show how combining the models improved the classification precision. The ROC curves demonstrated the model's ability to distinguish between the classes. The SVM had the highest AUC among the base models, followed by CNN with RF trailing behind. Among the ensembles, the averaging model had an AUC of 0.96, while the second ensemble achieved a near-perfect AUC, which confirmed its superior class separation capabilities. Looking at the CNN training, it showed steady improvement across all 5 folds. The accuracy rose to 0.8854 by epoch 37, where it eventually plateaued, with validation accuracy stabilizing at 0.8661 and early stopping being applied. Training and validation loss also decreased consistently, showing strong learning and generalization. Now, reflecting on the findings, the SVM and RF, being traditional models, were better suited to structured data and could not learn new features from images, which explains why they underperformed compared to the CNN and ensemble models. The second ensemble model outperformed the individual models significantly, achieving an accuracy of 96.85%, which was 9.66% greater than the highest performing base classifier. This was largely because the meta model allowed the ensemble to correct individual errors by each base model. The averaging ensemble, while still effective, only had a 4.27% increase from the current highest error among the base models. This was because it simply combined the predictions of the base models on the assumption that each base model contributes equally, which did not fully capitalize on the diversity of each, and that explains its slightly lower performance compared to stacking. Despite the strong results demonstrating the superiority of ensemble methods in this scenario, this study had several limitations. The small dataset size and simplicity of the traditional machine learning models restricted the performance of both base and ensemble models. Additionally, while the ensemble approach improved the interpretability by revealing how base model predictions are combined to a certain degree, it still inherits a lot of those black box elements from the CNN that makes it less interpretable than using just an RF or SVM alone. To conclude, the study contributed metrics on image classification that could be useful for the early detection and monitoring of cancer progression after stem cell transplantation in a clinical environment, which could then help physicians make more reliable and confident diagnoses, especially in complex or ambiguous cases. In future work, to address the existing limitations, researchers should experiment with more complex methods or feature extraction methods aimed to increase the interpretability of these ensembles without compromising accuracy, and use larger or more diverse datasets that improve model generalizability for these classification tasks. These improvements will be necessary to further improve the accuracy and robustness of ensemble algorithms when classifying stem cell stages, potentially contributing to more effective and safer biomedical applications. Overall, it allows clinicians to easily identify cancer development in stem cells, leading to more targeted treatments and better patient outcomes as a whole. Thank you.